Right. So today we have Sebastián Franco tell us about twin quivers, polytope mutations, and quivers for GTPs. Take it away.
Okay, thank you. Thank you everyone for the invitation. Thank you everyone for coming in a special day. I really appreciate it. I'm very happy to talk here today. First of all, because there are lots of friends in the audience, so it's a friendly audience, I hope. And also because there are many people that know a lot about the things I'm going to say. So, I mean, hopefully they can appreciate it. And the idea is also that for the other ones, other people that don't know so much, at least they get a feeling of these ideas, and maybe people get excited, we talk, that would be great. So what I'm going to talk about today is based on a recent paper with Rak, who is here in the audience, and some work in progress with Diego, who is also in the audience. Okay. So very good. So let me give you an outline of the talk. I will, start with a very, very brief introduction of, why we want to do what we are doing. I'll give you a roadmap of what I'm going to talk. I'm going to talk about a lot of things. I'm going to talk a little bit about what's called bipartite field theories that can be regarded as some natural generalization of dimer models or of brane tilings that will be important for what I say. I will talk about mutations of quivers, mutations of polytopes. Then I will introduce two sets of objects, polytopes, quivers, and the mutations of these objects with certain relation between the two. And I will, many of these objects have been studied at length in the past, and I will argue that it's important to investigate the two sets more democratically. And trying to study these sets democratically will lead to new questions that we didn't often consider before. And I think that that's the take-home message number one is this story. But then I will talk about one natural direction in which we took these ideas, which is that we talked about generalized toric polygons, and we assign some quivers to them. And I will provide some evidence why we think that these quivers are naturally associated to these GTPs. At the end of the day, it seems like it's a rather basic proposal. Of course, there are other edges of this proposal which are very interesting in my opinion. I will give you an example of how the S rule is captured by these quivers in a simple way. And then I will conclude. And as I said, please feel free to stop me. Hopefully we are more or less flexible with the time. So, I don't need to tell you that, there are these beautiful constructions which are called brane tilings or dimer models, which encode the four-dimensional gauge theories on DC branes when probing a Calabi-Yau threefold. They are given by bipartite, they are brane configurations, and they can be represented by bipartite graphs on a torus. Here, this is an example. The two sides, the opposite sides are identified. This not only tells you what the gauge theory is, but it also allows for a simple connection to geometry back and forth. It simplified many problems. So in this context, we have this set of objects, some toric Calabi-Yau, which is represented by some toric diagram, I might call it polytope at some point, some bipartite graph here. So these are the types of objects that we are going to be discussing today. But you also can consider the same geometries to engineer five-dimensional conformal field theories. And the quiver gauge theories described by this object also play a role there because they encode the BPS spectrum. So these objects appear in two interesting contexts associated with the same geometry. As I said in the summary, we're going to say many more things about these ones, but this is just these objects. This is just an introduction page. But then, in the study of five-dimensional theories of brane configurations, basically webs of branes and 7 branes, Francesco, Sergio, and Tachikawa introduced this kind of diagrams, which nicely capture some information about those webs. that one can imagine in some generalization of toric geometry. I don't know, at least the pictures look similar. But now with different types of dots here. So I think it's very natural question to ask, if this looks not totally different from this, where there's a natural generalization of brane tilings or the type of object that correspond to these ones that are associated to this type of objects. And if so, what are the applications are. So we're going to talk about some of these things today. So let me spend a few slides talking about bipartite field theories. Many of you, most of the things that I'm going to say, you already know them, but they're important to set up the language that I will use. A bipartite field theory is a Quiver gauge theory. You can think it as a four-dimensional n equals to 1 supersymmetric gauge theory, defined by a bipartite graph on a Riemann surface, which might have boundaries, right? So the brane tilings are an example, they're on a torus, but then you have something a little bit more general. So this is an example of a bipartite graph on a disk. And the way to construct the corresponding gauge theory is the usual thing is there is a quiver which is dual to this graph. In this case, you will have 6 nodes, which are the 6 nodes here. In this particular case, there are some nodes or some faces which have components which are on the boundary. These are like open faces, if you want. This corresponds to frozen nodes or global symmetries, if you want. And every edge corresponds to some bifundamental or adjoint if the periodicity of the surface is such that you have the same face intersecting with itself. And the plaquettes here, or the smallest closest loops, which are dual to these vertices here, except the ones that are on the boundary, correspond to superpotential terms. So that's the usual dictionary that you would use for brane tilings. And so the dictionary is that internal phase corresponds to some symmetry, subgauge symmetry group, some external phases corresponds to global symmetry groups. Then you have bifundamentals or adjoints for every edge. And if you have a node of which is k-valent, you have a term in the superpotential which involves all those fields. And we can also scale things in such a way that the white nodes corresponds to, let's say, plus signs, and the black nodes corresponds to minus sign. These theories are interesting because they have a very still rich but very constrained structure that comes from the fact that they come from these bipartite graphs that allows for connection to a lot of combinatorial objects that I will discuss and some toric geometry, right? It's just because of how they are constructed from these graphs. Very. So let's go over some of the basic ingredients that you would use when considering some of these theories. And again, this is a list of the natural objects that you will construct. For example, if you were a mathematician talking about these objects, all of them will have a physical use for us. If I gave a talk about just these theories for a more general audience, I would spend more time discussing all of them. Since this is an expert or semi-expert audience, it will be more like a lightning class. But the important thing is that all these objects are important. It's not that I'm just listing random objects that I define for a bipartite graph. So the first one is a perfect matching. And a perfect matching is a subset of the edges such that every internal node is the endpoint of exactly one edge in the perfect matching. Okay, so you take your edges, you take collections of them, and you make sure that all the internal points are covered. And there is a natural map that goes to the old days of dimer models that we are going to use here between perfect matchings and but the bifundamental fields in the quiver, which says that it's very useful to think about every bifundamental field as in terms of the perfect matches, where you include a perfect matching here, meaning you have an exponent 1 if that perfect matching contains a given chiral field. So a chiral field x1 might be a product of 3 or 4 perfect matches, which are all the perfect matches that contain that chiral field. This is a very convenient map of variables because it guarantees, it automatically satisfies all the vanishing F terms that come from the superpotential defined by the graph. And that, it has an important role in the connection to toric geometry because of that. Then I will also talk about zigzag paths. We have these graphs on a surface. Since they're embedded on a surface, there is, you can talk about turning right and turning left, which you wouldn't be able to talk about that if you were not on a surface. And you can think that there are 2 basic classes of paths that go over the edges. One is the path that always, every time they reach a vertex, they turn to the same side. Let's say they always turn left or they always turn right. Eventually, you are going to come back to the original point. These are what we call a phase. Well, of course, you can also include the open faces. That's totally fine, or the external faces. And there's another
question. Sorry, the small p is what? I mean, the big
small,
P is 1 or 0. It's a
right. A P is a perfect matching. A perfect matching is a collection of the edges on the graph.
Yeah.
So here you have a graph.
Yeah.
And you have it's a collection of the edges on the graph such that every node here is contained, every internal node contains exactly 1.
I understand, but in your formula for xi, or the small p's, the ones that are half
these are the
powers,
perfect matches, yes.
Are these numbers or what are they?
I associate a variable to each perfect matching. I said it's going to be.
So it's like some fugacity. Okay, fine.
Yeah, right.
Okay, thank you.
Thank you.
Not fugacity.
It's not fugacity. It's like it's a field. Yeah.
Complex field assigned to each perfect match.
Exactly.
Okay, but it's not physical. There's no physical interpretation.
It has a physical meaning. If you were solving for the moduli space, at some point you would express into some things in terms of some other fields, and these are the ones that are going to turn out there.
Okay. Okay, thank you.
Right. So, and the other set of fields is a set of paths is one that turns maximally right and maximally left, alternating at each vertex that they encounter. Okay. They can be nicely implemented in a double 9 notation. So here, let me tell you what you are seeing. So here the green lines indicate the unit cell. So this is a graph on a torus in this case, the usual brane tiling. It consists of 2 square faces and 2 octagonal faces. This is one of the toric faces of F0. You can think in terms of having the path on the edge. There's a convenient way of thinking about it in which you think that the paths cross the edge at the intermediate, at the middle point, and you have 2 zigzags going through every edge because you can go in one direction or the other. And this double line notation is a very convenient way of representing a zigzag path. So, for example, if you the picture might be a little bit difficult to see, but if you focus on eta 4, so here we have 4 of these zigzags. It has 4 faces and 4 zigzags. This doesn't need to be the case, that the number is the same. But as you follow the green one, you see that you turn right, you turn left here, you turn right, you turn left, you turn right, and then you close. So it goes around the torus with some winding numbers in this case, and it closes. Okay, any questions so far? Okay. Let's see what I have under here, the title, but let me. bipartite field theories are intimately related to some non-toric Calabi-Yau singularities. The two natural ones that you can associate to them are the master space, meaning the solution to vanishing F terms, and the moduli space, the solution to vanishing F terms and D terms. Both are toric. In the case of brane tilings, this one is a Calabi-Yau threefold. In general, since these are toric, you can define some polytope for each of them. It's going to be the toric diagram. They're going to come in different dimensions. Now, for general BFTs, the dimensions will vary, okay, of each of them. They will depend on properties of the graph and of the surface in which they're embedded. You can think about things that will contribute is the genus of the surface, the number of boundaries of the surface, and so on. Those things, you can express the dimension of these polytopes in terms of this data. And so it's totally general. It's not brane tilings. For part of the talk, yes.
Hi. So the connection with the toric Calabi-Yaus, is it just when the Riemann surface is the torus, or is for any Riemann surface?
No, it's for all of them. You will get some Calabi-Yau. I mean, whether you're not going to think in terms of a deep brane construction of some Calabi-Yau, because it can be like I don't know, 20-dimensional Calabi-Yau. But it's that. In the talk, or in the second half of the talk, I will focus on the case in which one of the two sides, at least, is on a torus for part of the discussion. But the ideas that we are talking about, I think are much more general. And again, perfect matchings and zigzag paths streamline the connection between gauge theory and geometry in both ways. If you are given one of these field theories with this very special form of the superpotential, and you want to compute that moduli space or that Calabi-Yau manifold, you will determine a very efficient way of doing that is determining the perfect matchings and then doing some operation on them, some projection. Alternatively, if you are given the underlying geometry, you can construct the graph on the surface by reverse engineering the zigzag path. This is something that people have done in math and in physics. Ami has done it with David Begg. There are many other papers, but it's also known from mathematicians.
Sorry, question. So what guarantees that it's a threefold? The fact that sigma is a torus and that it's a BFT together guarantees it's a threefold?
Yes.
I see.
Yes, and it's a two-dimensional toric point. If you want, there are many ways of doing that, why this happens, but from just a combinatorial point of view, you will only give coordinates to things depending on how they wrap on the two torus. So you will give two coordinates, two integer coordinates.
So for a higher genus, is there a simple relationship with the dimension of the Calabi-Yau?
Yes. I don't have it. It's in the paper. It's 2 plus genus plus the number of boundaries minus 1, something like that.
Okay, nice. Thank you.
And for the master space, you increase it a little bit. Okay. So let me say a few things about T2. The case of T2, the torus. The case when we are talking about the torus is the usual brane tilings. We get the Calabi-Yau threefold. We have the two-dimensional toric diagram. We have things that look like this. For later discussion, I will, whenever we have, I will use these two words to refer to the boundary of the toric diagram. I will talk about sides, which is any of these straight lines on the boundary of the toric diagram, and I will talk about an edge as each of these components in a side. So generically, you can, many times we will have toric diagrams in which every side consists of a single edge. but like in this case, we can have a side that consists of two edges, and these objects are dual just by graph dualization to PQ waves, and we're going to come back to them, in which for every if you can triangulate this object, and for every segment you introduce a perpendicular line here. Okay, so the fact that this side consists of two edges manifests itself with these two parallel legs here in the PQ web. There you go. More interestingly, in the case, so here you have a lot of objects, and again, I'm packing a lot of information for those of you that have, for many of you, it's a well-known fact. For some of you, it will come as new information. You can go back and read about these things. There's a brane tiling associated to this, or there are in general many brane tilings associated to this toric diagram. Those brane tilings have zigzag paths, right? And these legs are in one-to-one correspondence with the zigzag path, meaning that the orientation of the leg, that I will denote as eta I tilde, so I will use tilde variables to indicate edges of toric diagrams or legs of the PQ waves or zigzags, and I will use variables without tildes to indicate faces of the brane tiling. The orientation of these lines is given by a two-dimensional vector with integer coefficients. Those coefficients are literally the winding number of the zigzag paths, the corresponding zigzag paths. Of course, you can do an SL2C transformation of this, that that's represented by a change in the unit cell of the torus. That's a freedom that you have. But we're going to come back to this. Questions? So, I don't need to build the brane tiling for this toric diagram to know, first of all, that it has 6 faces, and that the gauge theory has 6 gauge groups, because that's the area of this toric diagram. But I also know that it has 6 zigzag paths, because the perimeter has 6 edges. Okay. Again, the fact that the two coincide is an accident of this example, but I already know this information from the start. Okay, so now let's talk about Quiver mutations. Again, we are building just the language of what we want to say later. For us, for physicists, the Quiver mutation corresponds to cyber duality. I will use the word. Quiver mutation is not just the quiver that we are going to mutate, we're going to also mutate the superpotential. So you have a piece of your quiver, you're going to, where you have a couple of nodes, a node here, there are some fields connecting to it, you might have many fields connecting to it on each side. I want to mutate on this node. So the operation on the quiver corresponds to replacing the original flavors by dual flavors, which have the opposite direction, meaning that if this was just super QCD, they will have conjugate representations under the global symmetry. And then you add meson for each directed pair that goes through the node that you mutate, you form a meson. So you can think about the meson as a composite of the original flavors. But then you also have to modify the superpotential, which means that every, the superpotential consists of many terms. Some of them might involve combination of fields that go through the mutated node. Here is, you have a piece that is xij, xjk. So you eliminate the passing through node j by replacing this by a meson. And then for every meson that you introduce, you add a cubic coupling to the superpotential between the mesons and the dual flavors. Okay? So that's the usual cyber duality rule. Sometimes, but not all the time in this talk, I will talk about connecting mutations that connect toric phases They're not special in any way. They're only special in the fact that they connect two theories that are described by bipartite graphs on a surface. Okay, and at some point we're going to go away from them, and they have a very beautiful representation, graphical representation. So, if in these cases, it basically corresponds to having a number of flavors, which is 2 times the number of colors. So the rank, by the way, also the rank is transformed. It's the total number of flavors being either the total number of incoming arrows or the total number of outgoing arrows minus the initial rank. So it's a cyber duality on a node that has a number of flavors which is equal to 2 times the number of colors. So, and again, you might vary these numbers, but I'm saying the 0th order statement here. So the new rank is equal to the original one, and they are represented, these transformations connecting toric phases are represented by this transformation on the graph.
Sorry, question.
Yes.
So when you have adjoints, I mean, this is always cited as a notorious problem for cyber duality. Do you have now a systematic way of doing that?
I won't mutate, thank you. I won't mutate nodes that have adjoints. Okay. Yeah, and I don't know how to mutate that unless you have some superpotential with some power of the adjoints. So I'm not going to do it.
If you have that, then you're home free, you're saying.
Sorry?
Then you know how to, if you have a super potential with powers of the adjoint, then you're saying you know how to do it?
No, I don't know how. I don't think that the power of the adjoints is going to appear in theories represented by graphs.
No, okay, but I'm also
right.
looking beyond toric.
We know how to do that, right? I mean, this has been done in the past. I mean, it's just pure super QCD. Right.
Okay.
You have the usual truncation of the chiral ring. You have several mesons which have different powers of the adjoints in them, and so on. Right. It has some Hanani-Witten kind of representation with multiple NS5s. Very good. So that probably suggests that it's probably a graph representation because this is like a higher dimensional version of Hanani-Witten. But again, so you replace a square by another square, which is suspended with some legs, which is suspended from the original graph. The fact that the 4 corners change the colors to preserve the bipartite condition is the reversal of the flavors. The addition of these legs are the mesons. You see that they have quantum numbers of the composites of the original flavors. These 3 valent corners are the cubic couplings in the superpotential, right? And furthermore, the original superpotentials that were here, they have the original flavors, pairs of flavors replaced by the mesons. So everything here is done by this transformation. However, I'm not going to restrict to that. So we are fine. Very good. So, so this is Quiver mutation. I will also talk about Polytope mutation. And for the sake of this conversation, I will only talk about mutation of 2-dimensional polytopes. This transformation that I'm going to discuss generalizes to higher dimensional polytopes. It would be interesting to see what things mean in that case, but I'm just going to mutate right now 2-dimensional polytopes. So again, remember, I'm going to have a polytope, or my toric diagram if you want. I'm going to label the edges with these I tildes, which is the same index that I'm going to use for zigzags, because I'm building some notation that it will become clear in a couple of slides. So let me call eta I the outward pointing normal to a given edge in the toric diagram, to a given side of the toric diagram, meaning probably a collection of edges. And I will call the number of edges on a side ni tilde. Okay. By the way, I can, the way I'm going to talk about things here is I'm going to take every side and I'm going to combine all the edges on a given side together. It's possible to do finer subdivisions. No, the discussion that I have here also applies to these cases, okay, with the obvious generalizations. This toric diagram closes or the dual web is in equilibrium, so they satisfy that the normals weighted by these ranks, if you want, and added them over an entire polytope are equal to 0, and I will introduce an intersection number between two edges, which is the usual thing. It's the determinant of the concatenation of the two vectors. Very good. So the mutation on a given side J is defined in the following way, right? You will take the side J and you will invert it. You will flip the normal to the negative of it. Then you will look at all the edges with the positive intersection, or if you want, all the, and we will see examples, all the legs with a positive intersection with the one that you mutate, and you will transform it in this way. Let's see what it does. It means that the new normal is equal to the original normal plus a contribution, which is proportional to the mutated edge times the intersection number. And all the other ones, the ones that have no intersection or negative intersection, remain invariant. And there is an alternative to this transformation in which you consider the edges that have negative intersection, which has the same formula, but you replace the intersection by minus the intersection. Okay, this is equivalent of doing cyber duality with the incoming flavors, or flipping what you call fundamental anti-fundamental representation and doing it with the outgoing flavors. Okay, and you also modify the ranks. You also modify the number of edges in a given side according to this way. Very good. So this formula should be suggested to a lot of people. It looks like any or most sociometric realizations of cyber duality have something that looks like that, and we're going to come back to it. So let me give you an example, right? So this is the toric diagram for del pezzo 1. Every edge here has multiplicity equal to 1. I gave you the normals here. This is 1, 0, minus 1, 2, and so on. And I'm going to mutate it according to, I'm going to mutate on this edge, right? Later on, I will analyze this example in more detail, and you will see that you have 4 different edges, and they come in 2 qualitatively different pairs, right? There are 2 edges that more or less the mutation looks the same, and 2 other edges which the mutation does more or less the same thing. So let's mutate on this edge, and what you obtain is the following. Okay, which is the same. It's in this case, which is very special. You obtain the same polytope, up to a flip. Okay, so let's identify things a little bit. So the red one is the one that I mutated. So it went from one side to the opposite side. The blue ones are the ones that didn't change because they have a given intersection, and the green one is the one that had positive intersection, so it changed to another number given by this formula here. By the way, when you plot things like this, it's very clear. I mean, I don't have to calculate the intersections to know, which edges are going to be transformed, right? So I draw the line which is parallel to the normal that I want to mutate. It divides the plane into halves. The edges that have normals that go on one half plane are going to have positive intersections. The other one that are on the other one have negative intersection. Okay. In this case, all the normals between, since this is an horizontal normal, everything with an angle between 0 and pi will be transformed. This is what happened here, and the ones between 0 and minus pi won't have a transformation. I can mutate Okay, this is a mistake. They shouldn't be together. Wait a little bit for this one. I can mutate on using the negative intersection ones. I can mutate, I can just change these ones. Sorry, these ones. And this is what you obtain, which up to SL2C transformation is the same polytope. Okay. By the way, here I'm introducing some notation. Oh, sorry. Okay. I call it mutation on H1 tilde of the polytope delta. Okay, I'm going to come back to that notation. Very good. I told you that there are other edges which have different qualitative behavior, so let me pick one of them. One of them is this one. This one here. So let me mutate with respect to that one. And what I obtain, if I apply the formula above, is this polytope here. Okay. Again, we can trace, you know, the one that I mutate, which goes to the other side, the one that doesn't change, which is the blue one, and the ones that change, which are the red ones. And in this case, I do need to change the ranks according to that. I get an edge with a side with two edges. Okay. It also changes the genus, you know, it changes many things, you know, in the number of internal points, but in particular, it changes things. And if you mutate, you know, if you change the edges that have negative intersections, you also have the same polytope up to SL2C transformation. Right? Question so far? Very good. So if you are thinking, I saw this with some, these two cases with some quivers in the context of DP1, you know, you're in the right track. We are going to recover this again. I'm trying to come back to this example as many times as I can, because I think it's a good example. Before moving on, let me talk about untwisting. You know, both mathematicians and physicists.
Maybe I have a short question.
Yes,
so,
yes.
So when you do this mutation on the toric diagram, are you changing the geometry? I guess you are, right? The geometry is not the same.
Yes, I am, yes.
Okay.
So far, it's something that comes to me with the same word called mutation, with the definition that seems suggestive to me, and I will make the connection soon. Yes.
So in principle, it has nothing to do with Samper duality, at least until now.
Yes, it doesn't.
Okay.
Very good. Yes, very good. Excellent, excellent. So, untwisting the six, so, you know, there's an operation which is called untwisting of six paths, which, you know, this is a beautiful paper that, you know, every time I read, and well, there are many papers. This is a beautiful paper. There are two beautiful papers here. I recommend that you read them, which does the following. But it's like a switch between the identities of these two paths, the types of paths that I described before. You know, the ones that always turn left or always turn right. You give this path an order to now start alternating what they do at each corner or each node, and you take the paths that like to go in both directions, alternate between two directions, and you tell them to always turn in the same direction, right? So what it does at the level of a given edge, you know, here you have the two zigzags that cross over an edge, and you replace them by a face. Now you replace it by something that goes straight. This procedure, of course, preserves the graph. It doesn't change the graph, but if you want to account for this change in how these things turn from left to right, you have to generically change the surface in which this graph is embedded. Okay? So this procedure takes faces and turns them into zigzags, and zigzags and turns them into faces. And as I said, the graph remains the same, but it's embedded on a surface generically changes. And it was very interesting because it turns out to be related to mirror symmetry and how people constructed diamond models using mirror symmetry, right? For brane tilings, it's related to mirror symmetry. Let's say for this toric diagram, the new surface in which the graph that was the same graph of the brane tiling is embedded is literally the graph which is given by the zero locus of the Newton polynomial, okay, which is the surface that plays the most important role in the mirror geometry. Okay, of course, you see here that also this guy kind of looks like an inflated PQ web, right? There's a PQ web that is the skeleton of this thing, right? And it's the PQ web which was dual to this graph, to this toric diagram, and that will also play a role when we talk about things on T2. But now you have a graph that is embedded on this new surface sigma tilde, like the same original graph. So you can apply your same dictionary of the first slide and say that this defines a new bipartite field theory, which I will call Q tilde. I will, even though I use Q and sometimes I will use the word quiver, it's important that this is the full theory. We know the quiver, we know the superpotential. So these surfaces, these graphs on more marginal surfaces, were discussed in the paper of bipartite field theories, and also Ami and Rack talked about them just for this specific context, the context of untwisting, for what they call specular duality. So summarizing, you have a theory Q, which is defined by a graph G on sigma, and twisting turns it into a theory Q tilde, which is defined by the same graph on a new surface, which is sigma tilde. The zigzag path eta tilde becomes a gauge group or a phase by untwisting, which I will call I tilde. Or if you started from this side, a phase I tilde is going to become a zigzag path eta tilde. And a phase or gauge group here, I, is going to become a zigzag path I. So you see, I use the same index for the zigzag paths on one side and the faces on the other one. And here, the zigzag paths on this side and the faces on the other one. The two sides are totally symmetric, so there's no initial side and the untwisted side. If you call the original side this one, well, by untwisting you obtain this one, but then you untwist and you go back, so it's absolutely symmetric. Questions? Okay, very good. So these objects, as you can imagine, I'm going to argue that they can be organized in two sets. So I talked about polytopes, I talked about quiver theories, I talked about mutations of quivers, and I talked about mutations of polytopes. And then I talked about untwisting. So these objects, the polytopes and the quiver theories, and their mutations can be organized on two sides, which are bridged by untwisting. And I will give them two names. One is going to be called original, and the other one is going to be called twin. There's no one original side. I mean, I can start from original and everything is symmetric. So what do I have on one side? You have original bipartite field theory or theory Q, which is a quiver and a superpotential. I have a polytope, which has to do with the moduli space of this theory Q. It's the toric diagram of that moduli space. I have a mutation of that quiver, cyber duality of that quiver on a node I. And I can also talk about the mutation of the polytope on edge I tilde, on the side I tilde. And, as I said, I can also group things a little bit more finely, and I can talk about mutations on edges, but for the sake of the discussion, let me just mutate on entire edge, a side. And on the other side, I will have a similar set of objects. I will have a new quiver theory, we call the twin quiver theory, Q tilde. I will have a new polytope, which is the the moduli space of this theory. It's the toric diagram for the moduli space of this theory. I will have mutations of the quiver, which are going to be now mu of I tilde on this quiver. and I will have mutations on the polytopes on the sides, which are indexed by zigzags, which were the faces of the other one. Okay. Very good. So I have all these objects. Many of these objects and their mutations and the relations between them are things that we studied in the past, right? So for a long time, for example, we were interested in, mutations of the quiver, cyber duality of the quiver, and invariance of delta under it, invariance of the moduli space. This was the whole story of when we were saying, oh, you have a single toric data and you have multiple faces for it. This is what we were doing here. We were also interested in untwisting. I told you, we were talking about BFT, we were talking about mirror symmetry, we were talking about cyber duality. What I say now is that what we're trying to advocate is that you should study the two things democratically, symmetrically. Everything is as important as the other one, and you have to start thinking about what happens when you mutate something on the other side, which are questions that we typically didn't ask. Just going to what Francesco's question predicted, a very natural thing is to say, oh, well, let me see whether the mutation on a zigzag of the polytope has something to do with the mutation on the twin quiver. The mutation of the polytope on a zigzag has something to do with the mutation of the twin quiver on the corresponding face. Right? It certainly doesn't have anything to do with cyber duality of the original theory, but we are all suspecting that it has something to do with the cyber duality of the twin quiver, and that's the punchline. Okay, so let's think about that.
Seba, just one question. Are there cases where the original and twin are the same?
Yeah, yes, they are. And I will give you an example that it's purely chosen. But yes, I try to avoid these things. But yes, there are some, and this was very common. Actually, if you look at many of Ami's papers, my paper, things from many of these ideas, have been inspired by those early papers, so have been floating around. And I think that there was, at that point, we have an incomplete understanding. First of all, there were no dimers at the time, so the role of untwisting was totally not there. And if you think about reflexive polytopes, these polytopes that have only a single point inside, the dual is also notorious, right? And most of these, so it's not clear where you are talking about Q or Q tilde in many cases, right? So we were transforming things and we said this is cyber duality, right? But the honest thing is that you have to think about the twin quiver, which generically it's very different from the original one, and that's the quiver that you are mutating. In this case, the two things become dangerously overlapping, not fully overlapping, but dangerously overlapping. Right. And yes, and typically, I don't know if it's a theorem, but there's even, I think it's a folk theorem that all these guys always have a phase which is invariant under untwisting. Like kind of minimal. Very good.
Sorry, I have another question.
Yes.
So you start on the torus, and so the zigzag, to each zigzag path, you associate two coordinates because you look at the winding. So these zigzag paths become arrows, as you showed.
Mm-hmm.
But now, so the other path are faces.
Yes.
So how do you associate coordinates to the faces? Because when you do this procedure, you go on the other side, it should become a zigzag path, and so it should be an arrow in some space, I guess.
Right. So yes. So there are many ways. So that's a very good question. So I will be. I think that this story is very general, and we have to study all of them. We have studied many of these things. Part of it, today I will focus on some subsets of these things. So we can always give coordinates to these polytopes, whether we construct them with perfect matchings or whether we construct them with zigzags. We can construct these polytopes in different ways. So the way is, once you have a graph on, let's say, higher genus surface, of course, you will have additional coordinates depending on how this path winds on that higher genus surface. And there's also coordinates that come from the boundaries. You have to introduce a cut between boundaries, and there's a prescription. We analyzed that with Galloni and Mariotti long ago. If you use perfect matchings, the same is true. You can use your favorite way of giving coordinates to perfect matchings. You can think about the height function, things like that, or you can do the physical thing and apply the d terms that you have on that surface, and you will get the extra coordinates. Right.
Okay.
So, yeah. Very good. So let me give you an example of the two sides. This is a very poor example that doesn't do justice to this story, because in order to make the plots, I pick an example in which the two sides are on T2 and are two-dimensional polytope. Okay, this is highly non-generic. So this is a polytope, this is a DP2. You can associate one brane tiling with its zigzags. You have 5 of them. You see that I label the faces and I label the zigzags according to the corresponding edges here. You can check that we were careful enough to pick the ones that have the right winding numbers and so on. If you untwist, you generate this, which in this case is something that also lives on T2, which you already knew, because you know that the surface sigma tilde is somehow dual to this polytope. So it's not that it comes as a surprise. The graph is the same. You can count the edges, they are the same. You can look at the vertices, each type of vertex, quartic, cubic, they are the same. But in order to untwist, you have to change how it's embedded on the surface. It's also T2 in this case, but it's a different dimer model. If you compute the moduli space of this guy, you get this other one. And again, you see they have the 5 faces. There's the 5 edges that corresponds to the original 5 faces. You can see some things here, that after some time, you see, the edge 1 and 2 obviously are parallel, they don't intersect. They correspond to faces 1 and 2 here that are sitting apart, they don't intersect. Right? So you can go back and forth and identify all the properties of each on the other one. Okay? Very good. In this case, you see there are no things that don't intersect. So that's reflected by this dimer and so on. And if you just want to represent the quiver, these are the quivers. It doesn't matter, right? I mean, but you can count the number of arrows here. They have the same number of arrows here. In this case, they happen to have the same number of nodes because the area and the perimeter of this story diagram are the same, but it's accidental, and so on. But when I talk about Q and Q tilde, many times I will draw the quivers just for space issues, but we're really talking about the full theory, the one that is described by this guy. Very good. I don't see what the okay, GTP. So I'm doing very well with the time.
I think it's okay.
People can leave, except my friends. From my friends, I went. Right. So Francesco wrote this beautiful paper. They were studying branes of PQ5 branes ending on 7 branes. And they introduced this notion that they call dot diagrams to tell you more or less capture the S rule and how the branes ended on 7 branes. Also, Sakura and Antoine talk more about the connection to toric geometry and so on. And these diagrams are as follows. So first of all, let me go back to the original case. Let's imagine that you have a brane a web of 5 branes without any 7 brane, you can think that the toric diagram, which is it's obtained by just dualizing this way. So that's an ordinary toric diagram. In the GTPs, white dots indicate that more than one 5 brane can end on a 7 brane. So, for example, in this case, it looks kind of a toric diagram that you have this white dot that tells you that these 2 branes, which are perpendicular to this edge, to these 2 edges, end on the same 7 brane. And you have more complicated things like this one. So here you have 2 that terminate on the same, 3 that terminate on the same, 2 that terminate on the same. Right. So one thing that I want to tell you I know that this is clear to many by now is that the polytope mutation that I was talking about is really the mutation of the brane web. When you move branes around, the way I like one simple way of thinking about this thing is that the 7 branes come, and again I'm just doing the 2-dimensional case now, and that's there was a general story, and now I'm talking about these objects. The 7 branes come with a cyclic ordering, and I want to modify the cyclic ordering. I want to take a 7 brane and move it to the other side. And one of the ways that you can think about this is that you're moving it over, either the bottom half or the top half of the other 7 branes, and you have to modify them. The other way is, you just move it to the other side. The 5 branes go through the branch cut of the 7 brane, and they modify the slope in a way that is like if they were coming from a different 7 brane. So this is one of the examples that we considered before, the mutation on this edge using modifying the edges with negative intersection. Well, this is like moving this to the other side, modifying the ones that are at the bottom. The 7 branes that are at the bottom. But again, I mean, you can do this thing more rigorously and say, keep the 7 branes the same, but then the orientations are changed when I go through the branch. Very. So you see that we're already connecting this polytope mutation to something that seems to be useful. And now we come to connecting the 2 things. So, the transformation that describes the polytope mutation appears in geometric realizations of cyber duality, Quiver mutation. So what is the quiver that corresponds to the polytope mutation? You can think about it. You can first consider the case in which all the edges have multiplicity 1. But what you see, it is a quiver in which it would be a quiver in which every node should correspond to a zigzag path, right? Or an edge in the polytope, or the side of the polytope. So then the answer is clear. This is the twin quiver. So the mutation of the polytope on an edge I tilde corresponds to the cyber duality of the twin quiver on the face I tilde. Okay. So let's do an example. Let's look at DP1. This is the twin quiver of DP1. And going back to Ricardo example, this is not an ideal example because this one is literally equal to the original twin quiver, to the original quiver. But this is the one that you also obtain by untwisting. It's this quiver. In this quiver, everyone that has thought about it for some time knows that there are 2 different types of nodes. The ones at the top, which have nc equals to 2nf, we dualize those guys and we obtain the same quiver up to a rotation. This theory has a cascade in which DP1 goes around, very similar to the conifold. And there are 2 other qualitatively different nodes, which have 3 NC flavors. And dualizing that, of course, is going to give me something that is a non-toric phase. Of course, we already saw that when I was talking about the mutation of the polytopes. I told you there is an there are two edges, which if I mutate them, they give me the same polytope. Here, notice that 1 tilde is literally this 1 tilde. So if I mutate this quiver, I obtain the same quiver. This is what happens here. But I also, so this is what we're doing here. But I also know that if you mutate on 3 tilde, for example, this guy, or if I mutate in 4 tilde, I obtain this polytope, which is not surprising because if I multiply, if I mutate on this node, I will get this quiver here, you know, I have to blame rank. He picked yellow. The rank here is 2, right? So 3 tilde becomes rank 2. And by the way, all the intersections here, this quiver are the ones that are given by this polytope. So this is literally cyberplan. There is more. Here we know the superpotential, right? I'm not going to give you the superpotential, but I'm not just doing the mutation of the quiver. I'm telling you what the superpotential is in each case. Any question?
Yes, I have a question. So you just said that this is a non-toric phase, but how do I see that well, what I would call a toric diagram on top of it is not a toric diagram then? Or would you?
Very good, very good. So very good. So very well. First of all, I mean, you know that we use the word non-toric and toric in very wrong, in a very wrong way. Here by non-toric, I mean not described by BFT, or in this case by a brane time. That's what I mean. Yes, very good. Your question was spot on. Polytope mutation tells me do this and obtain that. I already pointed out that these two are very similar. Of course, 2 or 3 slides from now, I will tell you, wait a minute, we really don't want to rush and interpret this guy as a toric diagram. It's something that has these points, has these normals, has the number of edges, but probably is something else, which is the only other something else that I describe in this talk. So that's what we are going to see. Okay.
No, because in principle, what I'm saying is that in principle, this if you interpret it as a toric diagram, it would give you some diagram.
It will give you something, and we are going to really look carefully at what it gives us. Yes, very good. So I will do this example in whole detail, and I will try to match with this.
Okay.
And it's a beautiful story.
So related question. So when you say that you can go from this last quiver to this toric diagram with 2 internal nodes, are you assuming that all the ranks of the gauge groups are equal to 1?
When I don't say that I can go from this one to this one. What I say is, given this, the mutation of this polytope is this polytope. The mutation of this quiver is this quiver. And if I read this polytope as I will put 1 node per side with the rank given by the number of edges in the side, I construct this quiver. It's slightly more subtle because it's not very good. But I will say that I can almost construct this quiver directly from this toric diagram, really, but it's subtle in an interesting way. Some cases there are additional pieces that are not captured by the usual things that we would do to this diagram. All right, but you're all asking the good questions. Very good. Thank you. Okay, so now let's go back to again Ricardo's question. Let's think about delta. This actually should be delta tilde as a toric diagram. Okay. It's this toric diagram. I label every single edge. I put these 2 that are on the same side, I call them 3A and 3B. This toric diagram, there's no problem building the dimer model for this toric diagram, but we also know it has a name, it's X33. It's one of the YPQ Blomman at one point that Ami studied. The dimer is this thing. This guy does have correct 7 gauge groups, right? And it has 5 zigzags, right? Which is, you can have all the information here. This is the original theory. what do I do if I untwist? Well, if I untwist, it becomes something very complicated. You know, it becomes something on a genus 2 surface, which is represented here. This graph tells you everything. It tells you the gauge symmetries, the quiver, and the superpotential. I'm not going to write the superpotential for you, but you can read it from here. This tells you how you have to identify the different corners of this octagon to generate this genus 2 surface. And if you just want the quiver, it looks like this, right? And I wrote it in a way to make it maximally, first of all, you already know that this is not the quiver because it has 5 nodes for the 5 zigzags. You see that I call 2 of them 3A and 3B, which are next to each other here. And I put them together because it looks very similar to the 4-node quiver that I described for you before, if you think about the only thing that you can do with these 2 guys. Okay? Very good. So is everyone with me so far? Very good. So, very good. So it's very suggestive that I would have to do something with those 2. So, as I said, as Ricardo pointed out, I previously associated different twin quiver to the same polytope. I say it's this, right? And I call just 3 tilde this thing. So, you know, if we generate this polytope by mutation, it's not that someone gives me this toric diagram, says, hey, Sebastian, find the dimer model and the twin quiver. If we take at face value the mutation, which, you know, we're going to argue it's good to take the mutation at face value, and we say generate this quiver, you will generate a 4-node quiver, which is this one, which instead of having 2 nodes, we don't intersect with each other with rank 1 each, you have a rank 2 node. So there's something special about this node, this point in the toric diagram that I put here in red. And you know, the suggestion is that this is a GTP. That I have to consider these 2 edges as being combined into something, as if they were terminating on the same 7 way. We arrive at this proposal by considering mutations and this philosophy of, okay, let's see what happens on one side of untwisting and the other side of untwisting. We propose it's general. We are going to say that we propose that toric diagrams correspond to toric twin quivers, and GTPs corresponds to non-toric twin quivers. Okay. Comments or questions?
Okay. So just to clarify, the quiver on the right is the twin quiver of some non-toric Calabi-Yau 3, if I probe it with a D3.
It's
not the theory. It's not the theory in the 3 brane, but it's the twin of that theory. Or is it the theory in the 3 brane?
It's a theory that I obtained by untwisting the original quiver and mutating it with the mutation that is the mutation that lands on this point.
Okay.
Sorry, can you explain? So what's the untwisting? What's the low energy field theory interpretation then in general?
Well, I'm not sure. You know, I'm not sure. I'm not sure. I mean, there are a lot of things. You know. Right. So, in the case of the mirror story, right, what you are looking is at how the different branes intersect on sigma, right? At the origin of the, I don't know, the U plane or the W plane, I don't remember. And this is what gives you the quiver. You know, the zigzags are related to the tentacles of where the punctures where sigma goes to infinity. If you, well, there are many ways to see that, but you know, you can take the Newton polynomial, go to infinity along the amoeba projection. You go around one of these legs, you see what happens when a couple of terms in the Newton polynomial dominate sigma, and you see how that translates into the brane tiling. No, that's a zigzag path. You know, this is not a very physical way of thinking about it, but you know, it's all things that are true that I'm saying. That's how, you know, you can see, for example, that they correspond to the legs and things like that.
But are you expecting these to be IR dual? The theories you get from, I mean, when you have a twin pair?
What I expect is that, very good, excellent question. What I expect is that the theories that are on the same side and are related by mutation are IR dual. The other, cross and twisting, no, I'm totally agnostic about that. Yeah.
But untwisting is a means of obtaining a mirror threefold.
It is, yes.
Okay. So then why isn't it really just an IR duality? I mean, you're doing mirror symmetry.
Look, I think it's a very, I think it's a very interesting question that I haven't thought about it in detail. So I prefer not to tell you something that I haven't thought about.
Okay.
I think it's an interesting question.
Okay. Thanks.
Very good. So, you know, here I put the two quivers side by side. The quiver of thinking about this polytope as a toric diagram. The quiver as thinking about this thing as a GTP. You see what's going on. It's just the merging of these two nodes that become that node of a higher rank.
Okay. Sorry, Seba, I'm slightly confused. Before you were talking about sometimes when we have a toric diagram which is not on, well, if you have something which is not on genus 1, then you can have a higher dimensional Calabi-Yau. So before you showed this octagon, this looks to me like you should associate a higher dimensional Calabi-Yau to it.
Yes. And that would be the polytope delta tilde that I'm not talking about.
Okay.
Yeah. So
Thank
yes,
you.
I mean, I think that the story is much more general, and you know, after the general philosophy, I carved like a very small subset, larger than the one that we discussed before, of things. Yes. Very good.
Sorry, but sorry to interrupt again, but now this the quiver on the left, I mean, it's not conformal. Or how would you? I mean, or you don't think about this? I mean, if I just look at the ranks, it doesn't look conformal to me. But I don't know. Maybe.
Well, I haven't computed the beta functions. Yes, I would say. Yeah.
Well, you weigh out the 3 and C. You know, I have the impression. If you give the same ranks everywhere, then.
Well, it's cyber dual of
Yeah.
BP1.
Yes. Okay. Okay.
It's the same theory. Okay.
Okay. Well, yeah.
Very good. Very good. So these are the two quivers, and you know, you see that the procedure, the connection is, you know, you merge these things, which gives you an alternative way or algorithm to construct the quiver tilde for the GTP without using mutations, right? So because this way I had to land on this polytope by mutating something else. I have to build I had to build the brane tie or the BFT for that theory. I had to untwist, and then I had to mutate. So here it tells you that the way to do it is you think about the polytope that you want to talk about as a toric diagram. You construct the corresponding brane tiling. We have many tools to do that. You untwist. This is very well defined. And then you merge the nodes that you want to merge into higher rank nodes. Right. It's actually much more interesting than this. You know, we're looking at it with Diego. You know, this procedure also produced the superpotential of this theory. So forget about GTPs. This is the closest that I know that you can get to dimer or brane tiling description or BFT description of a non-toric phase. Actually, I would say, I don't say it's a closest. I think it is the dimer description of a non-toric phase. in the sense that you have an underlying combinatorial object with a prescription which connects to geometry, and that tells you what this theory is. I assume that there will be better interpretations of this procedure. Maybe it's a higher dimensional object, it's not a Daimler model, and all these projections that we do here are natural. But even if you forget about anything else, this gives you a way of constructing this theory using brane tilings and untwisting. Questions?
Can I ask, so the quiver with the merged nodes, I mean, okay, I guess you're saying it's work in progress, but if you have the superpotential, you can compute the moduli space. What threefold do you get?
Well, I would say that in this case, I would probably, no, this is the same as the cyber dual of a theory probing DP1.
Mm-hmm.
So, yeah.
Okay, so in principle, you don't get the same geometry as before the merging.
Yes. That's why I don't call these two things the same. Yes.
Mm-hmm.
Right. Very good.
Another question, sorry.
Yeah.
So on one side, you have a gauge group SU2N.
Yes.
And on the other side, you have these two groups SUN.
Yes.
So is there some way of connecting them by Higgsing?
Yes. So all this procedure is, and I guess at the end, probably, ideally, and we said that in the paper, is if you had an adjoint here, right, that you can turn on and Higgs by keeping the rank, right? I mean, and with that adjoint, you will also be able to come up with all the other boundary conditions that you would like to come up with.
But you don't, you're not writing the adjoint here.
No. I think it's missing. Yes, it's missing. I think that this is something that is missing, but it looks as if you had that. Yes.
Sorry, but it's not Higgsing. It's more like a gauge symmetry.
No. If you had SU2N with an adjoint Higgs.
Oh, okay. So from right to left, it would be Higgsing.
Yes. Very good. Right. So far, I told you two methods to build this quiver. I said, oh, you obtain it by mutation.
So,
yes.
Not to distract even more, but in the previous slide, yeah. So you said that there would be a Higgsing if there was this adjoint from the right to the left. While
Right.
Well, yes. While if we look at the 5D theory that lives on the brane web, let's say, then there would be a Higgsing from the left to the right. Do you have something to say about this opposite arrow? Is it some?
I don't know. I don't know if Diego
contravariant thing.
I don't know if Diego has something to say. Yes. Yeah. I don't know. Yeah. Sorry. You might merge nodes, but you're not going to Higgs two SUN groups into an SU2N group. Right.
No, of course not. But it's the opposite arrows.
Right. Okay. Very good. So so far we talked about these twin quivers by mutation. I said, oh, the non-toric quiver appears there by mutation. I gave you another method here. You think about this as a toric diagram, and then you merge. You think about toric diagram. You construct the corresponding tiling. You untwist, and merge. Many people in the audience can think that there's a direct way of constructing this thing, which is very trivial, which is, for every edge on the polytope, every side of the polytope, with ni edges, you put a node there, and then you add arrows according to the intersection numbers. That's a very good way to try to guess these things. It has some limitations. It's insensitive to the presence of bidirectional arrows or adjoints on the twin quiver, and we think those are important. And it also doesn't not produce a superpotential. So, you know, it's a way of doing things. You can think about it, and it might give something useful. I'm close to the end. So now let me say a few more things. Let me give you an example, and you can say, well, you know, you constructed these twin quivers. You gave me one method, which is you know, I think about this polytope as a toric diagram, and then I untwist, and then I obtain my theory, or the mutations also. But some of you might say, well, but you know, there might be multiple even toric phases for a given toric diagram. So this procedure is not unique in principle. So let's see what happens in an example in which this procedure is not unique. Okay, so let's imagine that I want to find the twin quiver for this polytope. Okay, and let's go over, and I'm going to build this theory using two of the methods that I described for you before. First of all, I will obtain this polytope by mutating this one. Now, this polytope is obtained by mutating this DP2 on H1. I specifically picked it for this example because I know that DP2 has two toric phases, so it's a nice example to consider. Okay. The brane tiling, now we had the brane tilings in the paper, so you have all the superposition. The brane tiling of this theory is one of the brane tilings of this theory. One of the phases, one of the toric phases of this DP2 is this quiver. Okay, and it has a brane tiling. If you untwist it, it gives you this theory, which I guess in this case is the same. And if you undo the mutation, if you do the cyber duality here on node 1 tilde, you get this quiver. Okay, so that would be one way of building it. So now say, okay, let's build it in another way, right? Let's first think about this polytope as a brane tiling, as a toric diagram. Let's construct the corresponding brane tiling. It will give rise to a much larger quiver. Right now we have you have 8 gauge groups. This is a quiver. This toric diagram has multiple phases that you can associate here. We picked a specific one, right? And the specific one was picked by using the algorithm by these two Japanese people. They wrote a paper. It's called The Formation of Dimer Models. In what they were interested in is, you know, if it's a slightly different problem than the one I was discussing today. They said, well, if I build a polytope, if I obtain a polytope by polytope mutation, let me come up with a prescription that starts from the dimer model of this polytope and produce the dimer model of the mutated polytope. That procedure starts from this particular phase, and I tell this procedure I'm going to mutate on 6-1 and produces a very specific toric phase for this one. Okay, so they are correlated by this algorithm. Okay. I untwist, again, you untwist the dimer model, and then, you know, here you have 1A and 1B, which are the two edges that correspond to these two nodes. You merge, and you obtain the same result. So these are the starting point and the answer that we want to get. We want to build the twin quiver for this polytope. Okay. So now in the next slide, I will do exactly the same, but considering a different toric phase here, which will produce a different toric phase here, and I will see what happens here. Okay, so that's what we will do. Very good. So let's start from the other phase. The other phase, so we do the same. We say, okay, this is obtained by a mutation on H1 or DP2. let me pick the other phase of TP2 for which we have the brane tiling. It's different. It's something that we studied in the old days. You untwist it, you obtain this. And you obtain this quiver. Okay? I will compare the two side to side next, but let me just say what the difference is. The difference is this bidirectional arrow. The difference between the two quivers is just this bidirectional arrow. And I will say a few words about that. So what happens if I think about, let's use the other method, let's think about this toric diagram, let's apply the procedure of these two Japanese authors, we get a horrible quiver, more horrible dimer model, we untwist, we obtain this thing, we merge the nodes, and beautifully we obtain the same quiver with the bidirectional arrow literally in the same place. Okay? By the way, I mean, doing this uses the full superpotential of this thing. You have to check which things become massive. These guys become massless. You don't delete them because you don't have the superpotential term there. Everything here checks a lot of things there. This is the initial, what we want to talk about. This is the answer. And we obtain the same results in the two paths. So the final results obtained in the previous slide and this slide, which were obtained from different toric phases here and here, differ in this case by the bidirectional arrow. Is this a surprise? No, I would say that this is the expectation, because in the brane tiling, cyber duality corresponds to deforming the zigzag paths while preserving the winding numbers. And once you do that, you only create intersections between zigzag paths in pairs. So the only thing that could happen here at the level of the quiver, not at the level of the superpotential, but at the level of the quiver, was going to, that I would expect, bidirectional arrows in different places, maybe many of them. But well, I can figure out how many from the very start. It's just given by the difference in the number of fields between this phase and the other phase. That's the well, this one and the other one. Okay, so that's what it is. So it's not a surprise. Okay? Yes, Greg.
Yeah, can I ask a question about DP2 and this bidirectional arrow?
Yes.
So if you go back one slide to the other toric phase.
Yes.
If I remember correctly from like when I studied this example before, if you look at the brane tiling itself, there's a way to draw it so that you have a two-valent vertex that would have a bivalent, a two-directional arrow between vertices 2 and 5 and what's called B in this quiver.
No, very good, very good.
If you do that procedure, if you do the two procedures you talked about here to that starting quiver or that starting toric diagram, do you also see the bifundamental cover?
Very good, but this is not that bifundamental. No, just yeah. So this is the bifundamental bidirectional arrow that appears here. It appears in the twin.
Yeah. Okay.
And it's not a two-valent vertex because these are literally not massive.
Oh, sorry.
I'm saying that these guys survive, and these guys are moved with the mutation on node 1. They end up here in the right.
Sorry, I said the wrong thing when I said two-valent vertex. I meant exactly what you said. Yeah.
Yes. So everything works, to the level of the details. Okay?
And so if we started with that on the previous slide as well, it would still go through the same type of way.
Yeah, everything.
Right.
Very good. So have the last slide. Let's give some more evidence. Of course, the mutations work in the just the way in which define these quivers. The mutation of the webs work in the right way. They capture that. So we expect that they should cover the S rule, or at least rephrase the S rule in some way, which is nice. The general GTPs can be decomposed in triangles and trapeziums, which only the corners being black. So let's look at one of these building blocks and see what the S rule of the violation of the S rules means in terms of the quiver. You can imagine what it means. The proposal is that the GTP preserves supersymmetry if there is no duality frame of the corresponding twin quiver that simultaneously has positive and negative ranks. You know, that would be like having branes and anti-branes, or a quiver that breaks supersymmetry. Right. So let's do the triangle. You know, you can take the triangle toric diagram. You can take it you can always put it in this form. You can put it in the most general way, you know, without loss of generality. You can assume that N2 is smaller, so the length of this size N2, the length of this size N1, the length of this size come from N2 and N1. Let's assume that N2 is larger or equal than N1. You construct a twin quiver for this. It's a triangular quiver of this type. And you can see what happens, for example, if you can do all the mutations you want, but you know, once you find one in which you know, this is violated, that's the end of the story. So let's mutate on 2. And you obtain this, where the rank is N1 minus N2, which is N is smaller than 0 if the triangle has not equal length. Which is the same condition that was found here. And you can do a similar story for the trapezium. So, you know, again, I mean, it's the same. You're going to mutate the PQ webs. It's going to, at some point, produce an anti-brane. And you know, here we see that as a negative rank of the quiver. Okay. So, conclusions. You know, we propose a democratic treatment of the two sets of quiver theories and the polytopes and the relations between the objects. We call them original and twin. We think that they have to be studied on the same footing. There are a few items that we haven't studied in the past, I think. We establish a correspondence between the mutations of the original polytope and the twin quiver. Equivalently, because the two sides are the same, is mutations of the twin polytope and mutations of the original quiver. We propose that non-toric quivers are naturally associated to GTPs. We provided some evidence, you know, mutations, S rule, which is connected to it. We said something about the symmetries in the paper. We introduced 3 algorithms to construct these quivers. The first one is via mutations. The other one is regarding as GTP as a toric diagram as an intermediate step. And the direct one, I think that this is important because I'm not sure that everything can be connected to a toric diagram by mutation. So you know, some things might be more inherently GTP. Interestingly, these constructions are the closest we know to brane tiling for non-toric phase. This is independent of that. I think it has to be, this part of the story needs to be studied on its own ground. We think they provide a good perspective. So where are the future directions or questions that we have that are open? You know, we associate twin quivers to the full GTPs. You know, if you have different tessellations of the GTP, how do they translate into these twin quivers? What are you doing there? Can you build them in terms of elementary quivers? And if so, how? I think that the most interesting, one of the most interesting questions to me is this one. You know, I gave you this, I proposed that, but what I'm interested in is the analog of the original brane tiling, right? You know, the guy that is going to give me the BPS quiver, if you will, in the usual case. Is there something that is untwisting? Which is the generalization of it? What is the object here? So this is to me one of the most interesting questions. There are many others that are interesting, and you know, maybe you know, untwisting play an interesting role here. There were some other papers in geometric realizations of this configuration with 7 branes. It would be interesting to investigate whether there are some cases in which the two things overlap, and if so, if they are connected. Okay, thank you.
Very nice. Thanks, Seba. Questions?
Yeah, I have a question. Thanks for the nice talk, Sebastián. So I just wanted you to repeat, because you already said it, but I kind of got lost. So what it was for you, the smoking gun, you said at some point we can clearly tell that these are two segments that are somehow merged into one, i.e. a white dot. I didn't understand what the symptom was. That,
no, for me, the symptom look, I mean, at this, depending on the level of rigor, you can take this as a proposal, right?
Sure.
For me, I think that the fact that you have these two mutations and that there's only one interpretation that would do the right thing of the connection between the mutations of the polytopes and the mutations of the quivers, for me, that's it. There are more things that we are seeing nowadays, and since we are recording, I can say some of them because I'm not going to be scooped, but
we can wait until the recording phase is over if you want.
No. Look, we do think that these phases are important. We do think that this, like the presence of these additional arrows are important because anyone paying attention will realize that this modifies the mutation of some other nodes, right? So with Diego, we believe that the point that you are in the extended Coulomb branch, for example, picks one of these phases. So it's not a choice. Yeah, because there will be some points in which some things are aligned in very special ways, and these arrows seem to do the job precisely. So, I think that there are many things that that can be understood in more detail, and that we are going to study in more detail.
So can you? So you say, but that's about the twin quiver, not the BPS quiver. But you say it's somehow the two, because of course, in principle, you would have. Well, actually, it's unclear to me whether you would assign a particular quiver to a particular part of the extended Coulomb branch. If you mean the 5D CFT, right? There is often one that is more natural, but then you can always.
So, but I would say, and I'm not saying that this is how it works. I think that the indication that that's how it works is that imagine that I told you that the web is more or less related to. Imagine that there are things that only have, so these are anti-parallel legs. That's why they originally didn't intersect. Okay, so there are things that happen when they are aligned. I would say that when you construct the surface sigma, you have to tune the coefficients in a special way to have those things align. Once you tune the coefficients in that specific way, and you construct the brane tiling by looking at the coamoeba projection, there will be only one brane tiling that will come out of it. I would guess, because it does all other kinds of nice things, that's going to be the one that is the phase that has to be.
Thanks.
Do we have more questions?
Yeah, can I ask another question? So I was wondering if you look at the special case of a toric diagram, which is just a simple triangle, so that the brane tiling is an hexagonal lattice. This is something where you can't do easy mutations because nothing is a square move. But using your procedures with untwisting, are you able to glean anything about what those mutations might look like?
Yeah, no, I didn't look at that. It's a nice example to look at because you know all the infinite duals of this thing. So I guess right. I'm sorry. Right. No, the twin quiver is too simple in this case because it's a bunch of it's 3 nodes with the intersection 1.
Okay.
So there's no much to do.
If you did a dilated version of the triangle, like you had near the end of your slides.
Right. So that's what we did. Yes. Yeah. So I don't know. It can be studied in more detail. I just built the quiver, and that's. I looked at the mutation that I knew was not going to work.
Yeah. Okay. Beautiful talk, by the way.
Thank you. Good.
Do we have more questions? Oh, if not, then let's thank Seba for this nice talk.
Thank you.
And we can go off the record.
Off the record.